Hi everyone, welcome to my channel. In today's video we are diving into denoising autoencoders, a powerful technique for removing noise from images using neural networks. We'll be working with the famous MNIST dataset and implementing everything from scratch in PyTorch. Before starting the tutorial, I want to show you a quick demo on what we're trying to achieve. Basically, we're adding artificial noise to an image, and the neural network is trying to remove that noise from the image. As we can see, it works with different levels of noise, and we can choose different numbers from the MNIST dataset. Let's start by importing some libraries and also setting the device we're using. In my case, I'm using an M4 Mac, therefore my device is going to be MPS. And we're also going to define a transform. We're going to turn everything into a tensor, and we're going to normalize our images. For this project, I'm using the MNIST dataset. Therefore, using PyTorch datasets, we're going to download it and save it into our project. And we're defining a function to add noise to our images. For this, we're going to add torch.runN using the image shape. And we're going to multiply this by a noise factor to control the amount of noise being added. And now let's visualize an image with different levels of noises added to it. So we can see that the noise factor goes from 0.1 all the way to 1. Now we're defining our autoencoder class. It will consist of an encoder and a decoder. In the encoder we can see that it has two 2D convolutions. So we're increasing the channels from 1 as it is a black and white image to 32. Then we're going to increase it from 32 to 64. And every time we're applying a batch norm and a ReLU activation. For the decoder, it's a similar process but backwards. We are reducing the number of channels and we're increasing the spatial resolution of the image. And instead of using a batch norm and a ReLU after the second transpose convolution, we use a sigmoid to constrain the output values of the pixels to the range from 0 to 1. I also created a dummy input tensor so I can pass it through the autoencoder that we just defined, just to check that everything's working correctly and we're getting the desired output shape. And I also created these two functions just to see how the spatial dimension of the images are changing as they go through the convolutional layers, both in the encoder and the decoder. In the next step, a model is created, sent it to the device. We also define our loss, our optimizer, our learning rate, and the number of epochs that we're going to use for our training. And we're also defining this function just to visualize the original image, the noisy image, and the denoised image produced by our model during the training and during inference time. For the training process, we are also defining two arrays to store the train and test losses, and for each step we are varying the amount of noise, and that way our model does not generalize to only one level of noise. After our testing loop, we can see that we're printing the train and test losses for each epoch, and in the first epoch and in every 5 epochs we're using the function that we defined to visualize the outputs of the model, and that way we can have a visual representation on how our model is doing along the epochs. And now to save time, I'm speeding up the video during the training process, and we can start seeing some visualizations. We can see that we have one in epoch 1, 5, 10, and also at the end of the training. Now that the training is done, we're visualizing our training and test losses, and we can see that we have a really good curve. And we also visualize the outputs of our model and the testing data, and we can see that it clearly denoises the images. And that's it for today's tutorial on the noisy autoencoders using PyTorch. I hope you found this video helpful and learned something new. If you enjoyed this content, don't forget to give it a thumbs up and subscribe to the channel. Thanks for watching, and I'll see you in the next one.